Hi, everyone. Thanks for coming. So we'll just get started. We're supposed to start with an introduction of ourselves, but Thunder did a really good introduction of us, so thank you, Thunder. So I'm a solutions architect at Databricks. I've been at the company for about 3 years now, and I specialize in machine learning solutions. So I've worked with a lot of our customers to build scalable machine learning applications with Apache Spark. And
cool. Can I have the microphone? Perfect, thank you. So my name is Tim Hunter. I've been involved for quite some time now with Spark. But mostly I've been working on making deep learning work well with Spark. So this talk is really presenting one possible application that we've been working on with customers to combine these two domains together, to combine the domain of geospatial along with techniques like deep learning onto this to try to build some new solutions. So this talk will be about geospatial imaging at scale, and also showing how Spark, how this field is going through, like a lot of other fields, is going through a revolution thanks to the new amount of data that is coming in, and how Spark can help, and also for the kind of typical pipelines that we have seen in the field. And we'll show you also a little demo to see what you can do right now with just with open source and publicly available libraries without doing much tuning. So of course, this is not this is not a new activity. You can even say that building maps is probably one of the most ancient data science and big data activity, because back then you had to send ships around the world, collect the data, and then assuming actually the ships would come back with information, then you would update your base map. And this has been critical for thousands of years for a lot of reasons. And this is, there has been already a lot of solutions built around that, because it is so critical for understanding and navigating through the world. But nowadays, especially during the last 2 decades, there has been really a shift from surveying and surveyors going around. This is, what ordnance survey started from, people going around the field, to much more automation, not only from plane and satellites, but also now huge fleets of satellites. So this picture, for example, is from the Planet Lab organizations, which has built now a constellation of 80 of the satellites that scan the world on a daily basis. So you can imagine how much data you can collect. And this is not even counting now all the possibilities afforded by putting a cheap SLR on top, a cheap camera on top of a drone, and then just going back and forth around specific areas. So this is all new data sets which can be massively collected, and now that need to be processed. So now, because it is so cheap to collect all this data, you have now a much wider range of applications beyond military and traditional mapping. So of course, you're aware of all the efforts that are being done for doing disaster recovery, such as quickly surveying a zone that has suffered from a disaster. But also, we have seen some applications where people want to regularly scan all the road networks, for finding some damages on the road, for example. And some other application we're aware of is looking at satellite pictures to figure out which roofs of which neighborhoods have the proper inclination for selling solar panels. This is the kind of thing that you can do now at an extremely large scale without having to send someone knocking to the doors across the neighborhood. So, of course, with this new data set and with these new techniques, new challenges come into play. So, as it is probably the case for a lot of you, with this new data set, you need to find some more cost-effective solution for processing this data. And the tools that have been traditionally used in this industry, such as PostGIS, simply were not designed for handling petabytes of very rich and unstructured data like images. Also, another problem which is more specific to this domain is that the geospatial requires usually a very complex tool, a very complex pipeline of very disparate tools to build and to put together. Because when you collect images, you need first to align them to make sure that they correspond to the area that you want to process and to map. Then you need to do also all sorts of image and color corrections. Then, for example, you can do object detection or do a lot of, and then incorporate a huge amount of metadata that you have typically with these images. So all these tools, which are typically handled by different toolboxes or different software, need to be put together in a much larger pipeline. And being able to make all these steps work together is really is typically very challenging. So here we're going to take an example to motivate this talk, which is, given a set of images, how can we find some vehicles in these images, and how can we quickly get a few insights from these images? And since we're in London, we're lucky enough to have some data set coming from Ordnance Survey to do that. So as an example here, here is an image that would be available, and we want to find not only all the cars, but then have some more broader and high-scale insights about what is happening.
So you might be wondering how Spark helps with your geospatial analytics. And the way we see it is Spark is the glue for your big data technologies that exist in isolation. So for every part of your pipeline, you might be using a different package. So for example, for image manipulation, OpenCV is really popular. Deep learning, I'm sure everyone has heard of TensorFlow before. And then for geospatial analytics, we have things like PostGIS, GeoMesa, and also Magellan, which is based upon Spark. And visualizations, we're just listing the two that we used for the demo, but there are lots of other visualization packages out there. So, Spark can tie all of these libraries together and help you scale it across multiple machines. It also allows pipelining in the sense that you're able to piece different parts of your pipeline together without having to think about how you're going to store the data or the intermediate data representation. So here is a visual representation of our pipeline. We're going to start off with some map data that's courtesy of Ordnance Survey. And it comes along with some XML metadata, which consists of information like coordinates, which we will use in our visualization. And then we're going to ingest that data, pass it into a Spark UDF where we do some transformations, and then pass that transformed data into a deep learning model. And then we're going to put it into Magellan, where we're going to do some geospatial analytics and then visualize and analyze. So this will be what Tim will be demoing later today, and we'll take a closer look at it. And so we're going to talk through each portion of the pipeline, and we're going to start with how we're going to parse that image data. So we do that with Spark 2.3. And with Spark 2.3, we introduced a new way to read and write image data. And this allows you to use the same schema across packages. So you might be using SciKit image, OpenCV again, or PIL. And with using image schema, it allows you to use the same schema across all these packages. So here at the bottom is a little code snippet and how you can read your images in with Spark in 3 lines. And after ingesting it, what we're going to do is to combine the image data set with our XML metadata, and we do that with a regular Spark join. And then we have 2 UDFs that we use here. The first one is to convert our eastings and northings, which are the unique British coordinates that the UK uses. I was new to that. So we had to convert them into international latitudes and longitudes. And then the second UDF does, it creates image chips and generates respective coordinates for each image chip. So to kind of explain what that means, on the left, we have a sample of our JPEG image. And this comes in a 1 km by 1 km square. And you can see that there's a lot of information and objects in each 1 km square. So in order for our deep learning model to be able to identify objects with our current hardware, we kind of have to split them up into little chips so that we can distribute it across multiple machines. So we do that by cutting the image up with Spark UDF, and then that's what you see on the right-hand side. That's a sample image chip. And then we generate the corresponding latitudes and longitudes for the bottom left corner and the top right corner. So now that we have lots of image chips from each image, what we're going to do is to put them through our deep learning pipeline. So we've seen tremendous success of image-based applications, and this means that there's more pre-trained models out there that you can use freely. And we are able to use these pre-trained models to quickly build your domain-specific models using transfer learning. And that's what we're going to be demoing today, where we're going to use a pre-trained TensorFlow model to quickly generate predictions on whether an object is a vehicle or not, or whether it's a bus, a car, or a truck. So this is just a sample of all the existing deep learning frameworks out there. Again, we have TensorFlow here. I'm sure you guys have heard of PyTorch and also Keras. And the challenge of using these packages is there's always this learning curve of getting used to a new package. And also, it's going to be challenging to distribute it across multiple machines. So that's where deep learning pipelines comes in, where it's an open source Databricks library, and it focuses on an easy API that integrates straight into Spark. And you're able to distribute it across multiple machines and also use it for your image transformation. And also, you have the author right here.
I guess. So after that, after we have extracted features from the images, objects and so on, then we need to be able to run some tasks to understand what we have found. And typically here, since we're working with geospatial data, we're going to use some libraries which are dedicated to this problem. So the reason for having for using some specific libraries is because in the world of mapping, you need to be able to do quickly some specific operations, such as finding all the objects inside an area. This is what we're going to do. Or, for example, aggregate all the points corresponding to roads, or finding similar objects which you find in different images. And for doing that, there's a number of solutions available. We're going to use here Magellan, which simply because it is open source, and also it's because it integrates very well with Spark 2.3, actually with all the Spark two lines of releases, especially because it has it does a lot of optimizations under the hood for building quickly some indices and being able to quickly infer some objects based on some geometries. So let me show you what it looks like in practice. So here we go. So I have here this cluster on which I'm going to run all the stages of the pipeline that I described. So we start by, so just to show you the context of it, we start by all these JPEG images here, containing all the images of coming from satellites. And here, for this example here, I took London, so that was about 400 images that we're going to process. And for each of these images, we also have a large amount of metadata information, and such as which square of London it corresponds to, who took the image, and so on. So this is a typical, and here, thanks to Spark, this is your typical ETL task, in the sense that you can load all these XML files using Spark. So here I have access in particular to the to the coordinates in the British National Grid format. So we'll need to convert that, and then so we can convert that and then associate to each of the images just this information. But we could add much more information in a production setting. So this is for handling the metadata. So far, nothing new. But also the interesting part now with Spark is that you can combine that with the images directly inside the same data frames. And Spark will be able to handle that all across the pipeline. So you don't need to separate the large blobs on one side along with all the more structured metadata on the other. So here, as you can see, I'm loading directly inside a data frame. Actually, let me zoom in a bit. I'm loading directly inside a data frame all the patches of, actually all the images that I'm going to manipulate. So as Raela was mentioning, in order to be able to run some object detection code on top of that, I'm going now to slice this image into smaller pieces. And in the process, I will need to keep all the information about what are the coordinates that correspond to that. So to remember what part of the image it was. And again, here, you just need to use some regular operation like joins and to put all this information together. so that you can have inside the same data structure the content of the image and all sort of information that you have coming from different sources. And Spark can handle that, at any scale. So let's build some chips. I'm not going to go through this code. Essentially, it does some slicing and dicing of the images, and then make sure that the coordinates correspond to them. So after we do that, we convert essentially our 400 images into about 60,000 smaller chips, which are more 100 meter by 100 meters, and then we can send that to an object detector. It is much smaller and much easier to use than an object detector. But really here, there is some code on the top to be able to do that. But what I really want to emphasize is that once you have written some code using here an NumPy and the Python imaging library, all you need to do is to call your regular, your usual suspects coming from Spark, and exploding and then manipulating, joining, concatenating. Spark will handle behind the scenes all the shuffling of the data for you, without having to worry too much about how to associate different data sources together. So at the end, I have a data frame which is about 50 gigabytes in size, containing all my images along with all the coordinates, as corresponding to these corners here, and then I have all the data corresponding to the images. And you see here how in a production setting, you could add many more information corresponding to where this data is coming from, how it was extracted, how it was processed, and store that and propagate that all along your pipeline to be able to do extra validations. OK, so here, just because I'm going to switch notebooks, I wrote it on a separate, I wrote it using Parquet. And what we found out is that the columnar formats like Parquet, for example, work very well in combination with Spark, even for storing this kind of data sets, because Spark has been optimized to be able to handle large byte arrays, so that you can just write all of that at once without having to do some further post-processing or separate the content that is structured from the unstructured content. OK, so now that I have taken all my images, I have cut them into pieces, to be able to run some object detection. Let's move on to object detection. So here I'm reloading these images, and here is how I'm going to use deep learning pipeline. So I'm going to use an existing model that was already trained for detecting objects on satellite images for a competition called XView, which was based on a few thousand images across the world, and that was organized by the US Department of Defense. And the baseline of this was made available as a TensorFlow model. So all I need to do here is take this TensorFlow model, apply it to each of the patches, and then extract all the information it has, and find all the coordinates corresponding to these patches. So in order to do that, after loading the model, I can call this class here called TensorFlow Image Transformer, coming from deep learning pipelines. And really, all you need to do here is specify the input. So here, this is going to be the chip. Specify the graph of the computation for TensorFlow, and then tell the transformer what you would like to have as an output for your data frame. And after that, this is your regular MLlib code you call transform, and it is going to create a Spark data frame containing all the detected objects. So no need to think too much about how TensorFlow is going to interact with my data. Spark is handling all the conversion from images to sending it to TensorFlow, and then getting some results back in array formats. So just to show you what we're going to have here, so we're going to have all the boxes corresponding to the objects, the classes, so is it a car, is it a train, something else, and also the confidence based on that, on top of all the information that we had before. OK, so after I run it, because TensorFlow bundles all the prediction together, I'm going to unbundle them and extract the patches, And again, this is just doing some data frame manipulation. So from this detection, I can find then all the objects that it has found inside the images. And really here, behind the scene, I am using a cluster. This is all running on a distributed cluster, and I didn't need to do any tweaking to figure out how to adapt the size of my machines in order to run that across large amount of machines. So here it also shows you what the little piece of image that it found and what it associated it to. So here you see the class 18 is, in this particular classifier, correspond to cars. So it's clearly very confident about a number of cars here. But as we go lower, then it's going to find some other things. Okay, so here you can see the kind of object that it found across all the images. Okay, and all in all, we're starting to talk here about big data. Here it found about 5 million objects, and each of them corresponding to some little patches extracted from the images. So what does it look like? So of course, now we need to be able to represent that. So what does it look like in practice? So for example, if we focus on the cars, at this point, we can use all the SQL arsenal coming with Spark and start to figure out, what are the, let's take, for example, all the cars and for which it is confident about, and then display them. And in order to see what it looks like, then we can start to do some proper data science on using Spark. So here I plotted a small heat map of where it found the cars. And do we have here some people who live in London in the room? Yeah, a couple. So I found some curious patterns. In particular, I found that, okay, so if you look at the heat map, so of course it doesn't find cars inside the parks, inside Hyde Park or Regent's Park, which is a good sign that the detector is working more or less correctly. But also it didn't find anything, I think, inside London. And a couple of people gave me some explanations, such as the fact that there is, I think, a restriction. I think you have to pay a toll fee to go inside London. Sorry? Just in charge? Okay. Well, clearly here you see there's less congestion. Yeah, clearly the congestion charge seems to be working according to this car detector here. And I think we are around here, the airport. Yeah, there's still a couple of cars. And one of my more local colleagues told me that the round here of circles correspond to the M25 highway that goes around London. So this is just, in a few minutes, combining a few of these technologies, you can find some interesting insights like that. So also, we're curious to see that if you look inside, for example, Hyde Park, it finds some interesting things, such as it decided that it had a car here in the water and and here in the middle of the woods. So this is where actually using Spark can really help, because now we can start, now that we have all the coordinates of these objects associated to them, we can start to do manipulation based on proper geospatial toolings. So at the third notebook here, we looked at these elements by doing some GeoLocalized queries. So I have built a small data frame here corresponding more roughly to the boundaries of Hyde Park, to see what was inside. And thanks to Spark, and thanks to also the Magellan interface, I can use this domain-specific language to filter all the elements coming from my cars that are going to be within the polygon of Hyde Park. And this is just writing your regular query on DataFrame. So I think it should run. And here also I'm ordering it by scoring to see what it's going to find. So this is all here objects that I can find in that I can find. Okay, so now it's running. Okay, so it found some cars for which it was very confident, but then if you start to look more at the bottom, for example, it started to associate, so from what I've seen, it started to associate some benches and some of the shadows of the bikers to cars. So this is, of course, not a perfect model. It was not trained on this particular data set. Yeah, here I think it's a couple of pedestrians, and you can clearly see the limitation of the data set. But now we can start to quickly dig, in a matter of minutes, into the performance of the detector, see how we can add some post-processing and pre-processing filtering on top of that, just by combining a couple of these technologies together.
And that's it.
Any questions? A lot of questions.
I have a mic, so 1 second.
A trivial question. Is this notebook available?
That's a very good question. I guess I can export it, and yeah, we can post it.
The data set is something we got from Ordnance Survey, so it's not something we can publicly share right now. But the code, we might publish it in.
Well, actually, we can. So based on the XView data set, we can provide. Yeah, we should provide. We're going to provide a notebook that will work on publicly accessible data for doing that.
Other questions?
What is the schema type that you use to store binary data inside
So
DataFrame?
it's a great question, because I think I just need to uncheck this box here, and this is raw binary format. It is uncompressed. So of course, this is not the most efficient representation you would want for durable storage. This is meant more for if you have a lot of ETL tables that Spark can quickly access and load into memory. If you want something more durable for which you care about how compact it is, then you need to convert it to JPEG, then it's maybe lossy, or PNG, or some other formats.
Hi, given that the sort of Spark is built on, I guess it's the unsafe version of the JVM, right? Are we paying a performance penalty given that most deep learning packages are built in Python? Or I'm just not clear exactly like particularly how you've integrated these two things, where the boundaries are, and I mean, with image data, is there like a lot of serialization going on, or can you clarify some of that stuff?
So I can give you a very short answer, which is the cost that you're going to pay is mostly doing memory copy of a few byte arrays corresponding to the image. The longer version is essentially what is being worked on with Project Hydrogen to optimize the shuffling of this data between the deep learning stack and Spark. In this case, under the hood, it is directly copying data from the JVM to a C++ library, bypassing completely Python, using the GNI interface, I think in this case.
Okay, last question.
Hi, sorry, it's probably a very trivial question, but why did you use Magellan instead, for example, for GeoSpark? Because I knew that there is also GeoSpark, and what led your question to Magellan?
I think Tim chose Magellan because he knows the creator of Magellan, but really that's it's not something that we've chosen based on like feature ability or.
Yeah. So essentially you can pick any of these libraries here. I picked Magellan mostly because I knew the author, and also because here I was just using a very limited subset to showcase how you can integrate it. And here this is just doing polygon with point intersection. You could do some other operation, and each of these libraries has pros and cons. I think in the case of GeoSpark, from what I remember, the interface is mostly RDD based, and here, for at least for most of it, from what I recall. And here I wanted to be able to integrate that with data frames, mostly to show what it looks like. But there's definitely a lot of possibilities here.
Okay, thanks, Raela and Tim.
Thank you.